Hello, my name is Damián Gibaja, and first I want to thank the organizers for giving us the opportunity to present this working paper. I'm going to talk about meta models and category theory in the transformation of semi-structured data. This is a joint collaboration with Rosa Maria Canton Roda. We are professors at the Engineering School of the UPAEP University. The outline of the presentation is the following. First, I'm going to explain why we are interested in establishing a relationship between category theory and model transformations. Second, to reach our main objective, we introduce the basic concept of category theory that we use to describe model transformations. Specifically, in part 3, we use category theory concepts to describe the transformation of semi-structured data into structured data. Later, in part 4, we present our main result, which is the application of the Yoneda's lemma to model transformations. We finish the presentation with the conclusions. As we know, model transformations are very useful because they simplify data management, but also we can use them to link different structures. In this sense, model transformations share features with categories. Category theory is the branch of mathematics that identifies the main properties of mathematical objects, but also categories contribute to connect different mathematical structures by means of their main properties. We are not the first ones that recognize the previous similarities between categories and transformations. Mavrock and Ryan in 2017 observed the similarities between computer science problems and categories, and they choose to apply categories for model representation. Specifically, they use categories to simplify nested codes. Instead of applying categories for nesting codes, in this paper we show that we can describe a transformation of an object exchange model into a unifying modeling language by means of category theory. This means that semi-structured data and structured data induce categories that can be linked through a functor. Even more, we generalize the previous application by using the Yoneda's lemma. This means that we can describe any model transformation by using the Yoneda's lemma, but also we can simplify the level of abstraction of any model transformation. To explain our results, we need to introduce the basic concepts of category. First, what is a category? As we mentioned before, categories link mathematical structures by identifying similar properties among mathematical objects. So, formally, a category is a pair composed by a class of objects and a class of morphisms. Whereas objects can be anything, a morphism is a link between two objects, x and y, where x is the domain object and y is the range object. Also, a category has an operation between morphisms that we call composition. The composition operation should satisfy two properties. The first one is the identity morphism for each object in the category. This identity morphism is neutral with respect to the composition operation. As we show in this slide, the identity composed with f is equal to f, but also f composed with the identity is equal to f. The second property, the associativity of the composition operation, is related to the order that we can compose more than two morphisms. So F composed with G and later composed with H is equal to F composed the result between the composition among G and H. One of the main advantages of using categories is the fact that they allow us to link different mathematical structures by using the main properties of their objects. To do that, categories need mapping concepts. So we need to introduce two important mapping concepts for categories. The first one is the functor. A functor is a pair of functions, an object function and a morphism function. The object function maps objects in C into objects in C'. The morphism function maps morphisms in C into morphisms in C'. It is important to note that the morphism image respects the image of the domain object and the image of the range object. Finally, the second mapping concept that we need to analyze the connection between different categories and mathematical properties is the natural transformation. Natural transformation is a map between functors. We need such mapping because we need to respect mathematical properties in a general abstraction level. As we can observe in this slide, a natural transformation generates a commutative diagram. This means that the composition between alpha y and ff is equal to the composition between gf with alpha x. So we have the same result from here to here than following the opposite direction. Concerning model transformations, these are a set of rules that describe how a source model can be transformed into a target model. In such rule, the level of abstraction plays a central role, mainly because the simplest way of transforming a model with a low level of abstraction is by using a meta model. Particularly, this is very helpful when we use the object exchange model specification. In this case, we perform a vertical transformation when we link models with different abstraction level. We say that a transformation is horizontal when the level of abstraction is the same. In this slide, we present the transformation of semi-structured data into structured data. We can perform such transformation because the object exchange model allows us to generate a structured data because we only focus on types and attributes instead of instances. Also, it is important to recall that the object exchange model induces a directed graph while the unified modeling language generates a simple graph. By the previous slide, it is easy to see that nodes can represent objects and edges can represent morphisms in the previous data models. Thus, we observe that a model transformation is a functor between a directed graph into a simple graph. In other words, model transformations can be seen as a link between categories. Also, it is important to emphasize that the previous transformation is a vertical transformation. We are mapping a low level of abstraction model into a higher level of abstraction model. So, can we simplify this data representation? Is it necessary a model transformation? Concerning the simplification of model transformation, the answer is yes. We can use the Yoneda's lemma to simplify the transformation between two models with different level of abstraction into a model with a lower level of abstraction. The Yoneda's lemma is a very important result in category theory because it establishes the existence of a natural transformation that simplifies any category into the image of an object in the set category. The set category is the category composed by simple sets. So the Yoneda's lemma implies that any category and their corresponding transformation can be seen as an object in the set category. In this slide, we can observe the graphical interpretation of the Yoneda's lemma. As we can see in the left hand of the equation, the Yoneda's lemma suggests that model transformation increases the complexity of any data structure. In other words, we have a higher level of abstraction as we use metamodels. However, the Yoneda's lemma allows us to simplify such transformation by searching for a set that summarizes the main properties of a semi-structured data. In other words, we can use the Yoneda's lemma to avoid any transformation that requires increasing the level of abstraction. By the previous slide, we observed that the Yoneda's lemma has important implications in the analysis of model transformations. First, it is important to remember that we introduce a model transformation between a first level of abstraction model into a higher level of abstraction model, a meta model. In this sense, we have a natural transformation from different categories at different levels of abstractions. Particularly, we have a functor between the category of graphs and the category of directed graphs. By using the Yoneda's lemma, we can simplify such functors and such natural transformations into a first level of abstraction. Specifically, it is enough to understand the main properties of a semi-structured data by using a simple set. In other words, it is possible to avoid a meta-model transformation to analyze semi-structured data. In the previous slides, we demonstrate that we can describe model transformations by using category theory. Particularly, we present an example concerning semi-structured data and structured data, which is summarized by a functor between the category of directed graphs and the category of simple graphs. In terms of computer science, such functor increases the level of abstraction. Although the example that we discuss is very simple, since it is based on nodes and edges identification, the complexity of transformations may increase when we have big data. We know that big data is characterized by volume, velocity, and variety. Then, sometimes it's necessary to perform several vertical transformations to analyze big data. However, the previous modification, the excessive use of transformations, may modify big data natural features. To solve this issue, we can apply the previous theorem. In other words, the Yoneda's lemma allows us to avoid the increasing of abstraction by identifying a set that summarizes relationship between data objects. Consequently, in this context, the Yoneda's lemma avoids and simplifies transformations. In this paper, we present the relationship between software engineering and category theory. Particularly, we discuss how category theory concepts can describe model transformations. We focus our analysis in an example concerning semi-structured data and structured data. With respect to our main example, we observe that natural transformations between functors simplify how software engineering identifies and works with data properties. Consequently, we can reduce the level of abstraction when we apply category theory methodologies. Specifically, when we apply the Yoneda's lemma, it's possible to reduce the abstraction level of models by focusing on sets properties. In future research, we pretend to investigate how do we code Yoneda's lemma to simplify the analysis of model transformations. Thank you for listening to these presentations. We are aware of your questions.